So I'm Lawrence Wellman, and I'll be talking a little bit today about decoding unseen, enhancing OT fingerprinting with Protodetect. So Protodetect's application I developed to address a problem that we'll get to, and so looking through things. So as was mentioned, this is my senior project for my master's. So just want to thank my professors, my family, my colleagues and coworkers who all gave input and helped work through this. So the process, kind of the way we'll go through things. So we'll start a little bit talking just about what network protocols are, how they work. Then we'll look at some common network protocol tools, and then we'll look at Protodetect and how it works. We'll start with network protocols. So hopefully you can all remember back to, as a kid, to when you got your first walkie-talkies. If not, I'm going to share a little bit about my experience. So as a kid, I was about somewhere between 8 and 10. I had a friend who lived just a block away. For my birthday, I wanted a pair of walkie-talkies. So I get there, my friend's there, we're opening presents, we open the walkie-talkies, we get them out of the package, we put in the batteries, the lights turn on. First thing we do is send my friend outside, we try and talk. Nothing works. So we get back together, we start looking at them, we realize on top there's a little knob, we change it, we get on the same channel. So now we can talk to each other. Send it back outside, we try and talk again. We can talk, but we can't hear each other. We don't know why. So we get it back together, we're starting to look at it, we realize the button on the side you have to push to talk, and you have to let go, more importantly, to actually hear what the other person is, what the other person's saying. So you have to go back and forth. So kind of through this process, through what we had seen on TV, we started to use certain words that they use there. We started to understand why they use these words. So over and out, or break, or read you loud and clear. You start to understand some of these words that they use, and you build this natural language that you use to talk to each other to make sure that you can both hear and understand what the other person's saying. So then we get to what is a network protocol. Simply put, it's a set of rules for communication between two application services, devices on a network. There's lots of different protocols. If you're not familiar with the OSI stack, hopefully you are, but it basically goes from your data layer, your physical layer, which is your network cable that you're plugging in, all the way up to the application, so something like your web browser that's showing something to you on the screen. So there's different protocols here, and for each layer, sometimes you'll encapsulate following layers in there, so you can actually have, for like HTTP, you'll have Ethernet, and then IP, and then TCP, and then HTTP, and then you may have more on top of that. So we're going to start with what happens when you go to your web browser and you type in a website. You go in, you type in a website, the web page loads, you actually see the web page. What does this look like on the back end? What is your web browser doing? So to start with, we have some code that it sends. We can see there on the top, we have a request line, so the get / HTTP 1.1, and then we have some information that basically tells the server a little information about the host that you have. Who you're requesting, so if there's multiple web servers hosted on one server, it knows which one you're looking for, and just different information about your browser so that it can kind of know if it needs to reformat something or change things a little bit, you can do that. So, similar to when you build this natural communications, here we have a standard. So to specify, so every browser, every server, hopefully can kind of understand what's being sent and what's being received. So for HTTP, it's RFC 9112. It's a very long document. It's got lots in there, and it goes over each little bit of what it does. So we'll show for that first line, that request line, kind of what it does. So you'll have that, the request line has the method, SP, which is just a space in there. You have the request target, and then the HTTP version. So from that get / HTTP1, the get would be the method, The request target is just that /, which is just looking for the home page, the index page, the default page for that. And then you have the HTTP version, which is the HTTP/1.1. So you build this, you send it off, the server gets it, and then the server has its own response. And so this, you'll have the top part, which you have that status line, which looks somewhat similar, but a little bit different. So you have the HTTP1, the 200 OK, you have some information about the server, and down at the very bottom, you'll have the actual HTML code that is displayed by your browser. You can kind of see, if you look in there, you'll see some parts of it. So the HTTP, home of the first website, some of that. And so there's this language that helps describe how the web page should look and how the browser should interpret it. And similar to the GET, we also have code or a message on how this should be interpreted. So we have the status line, we have the HTTP version, the space, the status code, and optionally the reason phrase, which is basically defining what that status code is. So for 200, you get OK. Basically says that everything's OK with your request and with the page that you're accessing. There you go. So we're going to simplify a little bit on kind of how it goes. So you get that text protocol. So the get / it gets converted to hex and then to binary and then to electronic signals that go across the wire. And then on the other side, it's going to go through the reverse of that. You're going to get the electronics, you're going to figure out the zeros and ones, convert it to that binary, to the hex, and then to the actual protocol that's being interpreted by the server. So here we start with one that was text. Next we'll look at, so not all of them are text and human readable. Some of them are going to be binary. This is a very simple one. This is UDP. So basically it sends a package, a message across to the server, and it doesn't care what order they're received in. It doesn't care if it actually made it there. It just sends it across. So here we have the source port, the destination port, the length, the checksum. Let's do this. So we'll load. We can see that we have there, for each of them, we have binary bytes or bits that lead to the different things. So we take so many of those, and they equate to something. So when the server reads it, it'll read those first 8 bytes, and it goes to the source port. And the next first 8 bits go to the source port, and the next 8, or not 8, 16. The first 16 will go to the source port, and then the destination port. And so as it reads this, it can interpret those, and then it can actually read and figure out what's being said. We go to TCP, and TCP not only has the bits and bytes of how the protocol is ingested, how it's read, but it also has a standard of how it talks. So this kind of goes back to the walkie-talkies that you need to establish that you're wanting to talk. So when it starts, you have what's called a SYN, or a synchronized packet that goes across. The server will respond with a SYN ACK, and then you send an ACK, so an ACK acknowledgement. So it goes back and forth and does this little handshake, and then once it's established the communication, then you can actually send data back and forth. It also has a finishing handshake that follows a very similar thing there. And so you'll have these bytes, and then they'll add up to this handshake. And so you'll build kind of a state machine of where you are in the protocol and what needs to come next to actually continue this conversation. All right, so now we've done a very simple, quick introduction to protocols and how they work. Now we're going to look at some of the tools, and they'll pull out some of the information for us. The first one we'll look at is Wireshark. It's kind of the big one. So we have the 3 different sections. So you have the top section, 1. This shows each individual packet that's sent across in the communication. On the left, number 2, or I guess, yeah, left for you guys. Number 2, you have the OSI layers essentially broken down. So you'll have your Ethernet and your TCP, UDP, depending on what protocol it is. On the right, you have your hex, and then how those actually interpret. It can be set up a little different. This is how I like to set up mine. And so now we're going to go demonstration just so we can see. Maybe. Oh, there we go. That turned off. Okay. All right, so we can see in here we captured the network traffic. I captured across my wireless interface. We can see we have lots of different things in here, lots of different protocols, and so we break it out. So we have the time from when we started recording for each packet, when each packet came in. You have the IP addresses, which is how you reference each other, or one way to reference the two different systems that are talking to each other. You have your protocol. This is what specific protocol that they're talking, the length of the packets, and then just a little information. The information will change depending on what protocol and what part of that state machine that it's in. And so I'll look for that HTTP where we loaded it. So we see here, we just have two packets. We have our initial HTTP. Some of that initial information we are going to get this page, the NCSI page, and then some information about the server, and then we get the server response, which is that 800, 200 OK, and then the actual content of the page. Since I loaded the page earlier, it doesn't actually look like it's in there, but yeah, so then that's that protocol where it goes back and forth, and we can actually read and interpret it here, and we can look at what's coming across the wire, all the different things. So when we're doing an investigation, when we're doing some of this or looking at different devices, then you can use this to actually identify the protocols and what's coming across. Let's go back to here. All right. So the important thing to point out here, so Wireshark, the main thing that it uses to identify its protocol, so what it's putting in that protocol section is the source and destination port. That'll come back to be important later, but that's something to point out. All right, so some other tools that we use that can be used for network protocols. Just go through a couple of these. Okay, I think we have two open. So we have Grass Marlin. This is an old, somewhat older tool now. It's actually been deprecated, but was put out by the NSA to help identify OT-specific protocols, to help identify kind of the environments, the networks, and what's on there. So I just have a repository of different PCAPs. We're going to come in here, open a DMP3 one, and we'll add that. Yeah, let's open. That's not an exciting one. Let's go. Let's do this one. So this will go through the PCAP. It will identify the different things that are in there, and it's going to display that. Almost there. There we go. And so it'll draw us a graph of kind of the different hosts on the that are contained within that PCAP, and identify how they're communicating. It draws that out. We can come to one of the hosts. We can right-click on it, and we can view details. This will tell us a little bit about that device, kind of who the manufacturer is, if you can pull that out of the actual traffic. And then here it'll talk about what protocol that is. So for here, that one's talking mostly Modbus. And so it identifies the different ones, it identifies the protocols, it helps point that out. And so we can use this to find some of those protocols and do some analysis on the network capture to figure out what's there. All right. And the last one we're going to show is here, is called SynSaber. We'll open that DMP3 packet. So you upload a PCAP. So this is one that they released just a couple of years ago to actually do this analysis. So you can go to the website, you can download it, and it'll do a similar thing to what the Grass Marlin did, where it'll draw your graph, it'll list your hosts, and then it'll identify the protocols. For some reason, it's being really slow. Let's close it out. Try to reopen it, see if that'll help. There we go. So we come in, it identifies the different assets, pulls out what information it knows about them, and then we get a breakdown of the different vendors. It wasn't able to identify the vendors in the specific PCAP we gave it, but it was able to identify the protocols. It said there were 8 packets that were all DMP3. So all these tools can be useful kind of as you go through. You have a network capture, you want to find out more information. Kind of from the previous talk, the knowing your network. This is kind of things that you can start to help identify what's on your network, how it's talking, who's talking to who, and then what protocols they're using. How are they communicating to each other? So this gets to Protodetect. So the problem that we had first, I like this quote. I didn't come up with it, but everything is made up and the ports don't matter. Kind of references a TV show that if you're using the ports to help identify your protocols, these are things that are configurable. People can change them and do for various reasons, security, just managing their network. If they have too many things talking in one port, they may separate it and have other ports so they can know what area it is or what environment it is speaking. And the more overarching problem that I was trying to look at is I run a lot of these security tools in my environment to help me look at network traffic, help trying to identify potentially malicious or things that are misacting. How do I know what they're missing? So as I look at this, a lot of it will show me things, and then you might run queries, you run my searches against it, and it returns and says, here's everything we found. So you know if it found something, but you don't know if there's stuff there that it's not missing. And so I wanted to start and figure out how I can identify what my tools are missing, what aren't they showing me. And so we're going to do a little demonstration. Go back to our Wireshark. Let's see, are they going to show up in all right, so this is a PCAP that was taken during another security conference where they had a lot of OT devices and different OT traffic. So I've made it a little smaller here, just extracted the OT protocols, mostly because that's specifically what I'm looking for my tool. But it runs on the other one just fine. It just takes a little longer and is a little more harder on this machine. So all right. So we have two versions of this PCAP up. We have the one over there. You can see that it identifies the protocols that we scroll through, scroll down to the bottom. We'll have a few different protocols. So we have Modbus, DMP3 is in here somewhere, S7COM. So it's able to parse the packet. You get different information. You can kind of see where it pulls for each of these. It can pull out and tell you some of the different parts of the protocol, what's in there, what's being sent across the wire. On the other side, we have the exact same protocol, or the exact same PCAP. I made one little change. I went through, and for each packet, I modified the source and destination port. I added 2001 to each of those. Why 2001? A lot of people will take a protocol and add a specific value to it. And so you might have HTTP that goes across to port 80. They may add another 80 to that, and if they're making changes and go to 8080 or 8000. And so I wanted something that's not going to be replicated generally across the specific protocol, because I'm adding the same value across all of them. I also wanted to take the lower ports, which are set, so your 0 to 1024 are set for most applications, and they're specified for specific things, and push them up into the ephemeral range. So I changed that, and then for the protocols, they'll have a checksum that says, hey, are all the bytes that went across the wire the same? So I had to recalculate that. And so that's the only changes I made, is I changed that checksum, I changed the IP, and now all of a sudden, Wireshark doesn't understand. It doesn't know what's there. So it still identifies the TCP. You'll still get the same, let's see if we scroll to the top. On each of these, this bottom that's showing the packets, it'll still have the same bytes there. It's still read it all. It just can't parse it. It can't understand what the protocol that was speaking there. And so, this is something that if you're doing in your own environment, you may know, you may say, hey, we're running S7COM on this specific port. That's non-standard. So Wireshark does give you the ability to go in and configure it and say, hey, we're running it on this port, search for this. Some issues with that, though. It doesn't give you the option for all protocols. Can you actually define that? It's kind of a manual process. You have to come in, come down to preferences, and then you have a long list of protocols. So you'd have to come down, find your specific one, and let's just pull that one up, and you can say, hey, we're running it on this port or ports. And you can configure it, and then all of a sudden it will be able to read and interpret it again. It doesn't do this automatically. You have to have somebody who can come in and look at this packet here and say, hey, I recognize that packet. It's S7COM. Some people spend enough time in the data that they can actually do that. Not everyone can, or you can if you have the application. But part of where this came from is I often will get PCAPs with very little to no explanation of what's in the environment, what necessarily is a PCAP. We just saw badness in here, or we suspect there might be badness. Here's a PCAP, go. And so you don't know what's in there, so you interpret it, and you run it through your tools. It reads through that. You see certain things, but back to that, you don't know what it's missing. You don't know what's in there that hey, all of a sudden it can interpret it. So rules that you may be looking for against SMCOM or Modbus or DMP3 all of a sudden aren't being detected because it doesn't recognize that as the protocol. So it may just say, hey, there's no Modbus in this packet. And there is, it's just on a different port, and so it's not interpreting it. All right. So for Wireshark, they have two different ways of actually detecting a protocol. The first is called link dissector. It basically has a line in there that says, we're looking for TCP port on 22, send it to the SSH handler. And so that's the primary way that it uses. It also has a heuristic dissector, which will check specific bytes looking for specific things. So we can see there on the link dissectors, you got 2,800 packets. So that's the only thing that they use, or 2,800 protocols. That's the only thing they use to identify the protocol. For another 271, they implement this heuristic detector to actually identify, hey, what's the packet look like, so whatever ports it's on. The problem is that most of those actually use the link dissector first. So you'll use the link dissector to say, hey, this is port 80, send it to HTTP. But for some protocols, they'll actually have multiple protocols that work on the same port. And so the heuristic is actually used to differentiate after you've looked at the port and identified that they're on this port. So identifying this problem as a problem, I developed Protodetect. Uses Scapy, which is a library that helps parse traffic, network traffic. And it also uses Community ID, which is a library that's put out by Zeek or Corelight or Bro, that basically takes the source and destination IP addresses and the ports, creates a value for those. So depend on your traffic, you'll have specific packets that go from the server to the client and ones that go from the client to the server. This just normalizes that so it's all the same, so that you can know this is that communication stream between these two hosts, and so you can pull out both of those. So we give it a PCAP. It examines that PCAPs, and then it tries to make a determination for each packet, what is this packet's protocol? What type of is that? And so it looks at each individual packet initially, and then it takes and combines those packets, those guesses for each of the packets in the stream to make an overall guess of, we suspect that this communication is HTTP or Modbus or SMCOM. It does that because, for example, what we saw with the HTTP is you'll have a few packets that build that communication that are TCP. So you'll have that SYN, SYNAC, ACK. Those are just going to be TCP commands. So you look at those, you won't know that they're HTTP. The rest of the communication will be HTTP. So if you take a look at the whole communication, then individual packets may not be identified as HTTP, but the overall connection will be. And then it gives two different types of output. It outputs to the console and says, here's the different protocols we detected between these two hosts. We saw this much. It also prints out a CSV file that can just be used to look through and say, for each individual packet, how did it make its determination? Specifically, what determination did it make for that packet, and what information is there? What are the bytes? How do we make our determination that this is that packet? There's lots of different protocol fields that we can use depending on the protocol. So the first is magic values. It has lots of different names for different protocols. It might be a protocol ID. It can just be start bytes. Then it's bytes that are specific to that protocol to help you identify that this is that protocol. Not all protocols will have that. Some aren't as useful as others. Some other fields. Length fields and CRCs are the ones I primarily used. I found those helped identify the protocol both the quickest and the easiest. But there's lots of other ones. You can have specific bytes that it says these are the only values you can have in that byte are 0, 1, or 2. because that's all we've implemented. All the rest are reserved for future use that either never get used or get reused for other things. You can have fields that are timestamped, so you can look and say, does this look like a timestamp that is valid for this given environment or for this thing? You can look, and so you can use some of these, put them together, and actually give a fingerprint. So we'll look at two different protocols. So you have Modbus. Here I use the protocol ID and the length. Problem with this one is the protocol ID for Modbus is 4 zeros. The problem with that is you're going to match, if you're just looking for 4 zeros in this specific spot, there's lots of other protocols where just in their normal act may have 4 zeros in that spot. So you can't, if you do just that, you're going to run and match against a lot of things that aren't Modbus. So the other thing we use is the length. And so the length field basically says how many bytes, and each length field's a little different, but for Modbus, it's how many bytes are after the length field, and it gives you that number. So we can use that. We can say, hey, look at this specific bytes in the protocol, count how many bytes are after it. If it's more or less than that value, it's probably not Modbus. So, and then we can combine those. And then we can make a determination and say, hey, we think this is Modbus. Then we have DMP3. DMP3 has a little better start bytes. So it's 0564. This is great because it's a specific thing you can look for and say, hey, does it start with this? If not, we throw it out and let other parsers take a look at it, or other matching for other protocols. You also have a length. Then you have some other things, and then a CRC. A CRC is basically just doing a checksum against the values. A simple way to think about it is if you have a list of 5 numbers, you take and you look at your first number, you say, is it even or odd? If it's even, give it a 1. If it's odd, give it a 0. And then you look at your next number, and then you take that sets of zeros and ones and use that as your CRC. And so if any of those numbers change when it goes across the wire or gets transmitted to somebody else, you can take that and you look and say, hey, is that first number even or odd? And is the checksum say it's even or odd? And match those together and say, oh, they don't agree now. Something must have changed. Please retransmit. Please send it again. CRC is a little more complicated. It goes through a whole bunch of stuff, but that's what it essentially is. And so here, the CRC, it's a little slower to calculate. You actually have to go through and do the math, calculate, hey, does this match over these bytes? But if it does match, it's very unlikely that's going to happen randomly. And so, for DMP3, you actually have multiple CRCs. So you have a CRC that does the entire protocol, or the entire packet, and then you have CRCs for each individual data block. And so you can actually check multiple of those CRCs to be more sure that it's there. But for all the PCAPs I had, just checking that first CRC was enough to actually throw out any. So we run this. We run through Wireshark is what I'm showing here, but we also did it for the Grass Marlin for the SynSaber OT detection protocol. We ran through, we loaded up, and so we said, hey, how much did Wireshark how many packets did it detect in this one PCAP? How much did Protodetect detect in this PCAP? There's some differences in those numbers if you look at them, and it's various reasons. So some Wireshark, if you have one that is not valid, it wasn't reporting it as that protocol. So if you have a Modbus that has the wrong CRC or some of the bytes are corrupted, it's no longer counted as Modbus, it's an error packet. So some of those Wireshark said weren't, Protodetect said, hey, this is still that protocol even if it's not formatted fully correctly. Some other issues that I ran into are packets that are too small. So you'll get some that in the protocol, it won't have any data bytes. It'll just have the initial header, which if it's a very simple header, it's going to be too difficult to differentiate that from other small packets from other protocols. But overall, I went through this, and then I loaded both the original PCAP, I saw what the numbers were, and then I loaded my modified PCAP where I added 2001 to each of the ports, and said, how much did it detect? Hey, for all of these protocols, Wireshark didn't. This is something I knew conceptually. I had done things. I realized that it doesn't detect these if they're on the different protocols, but I had never tested. I had never gone through and said. And one of the things that was interesting to me as I did this is OT protocols are kind of their own bag. Then there's ones that aren't documented. There's ones that have been built and used or still used, but the vendor who created it isn't around anymore. So no one fully knows how it works. They just know this is what we set up and it works. Don't touch it. And so I knew this was a case there. What I didn't know is that outside of a couple of protocols, so HTTP, it gets, as that get, or that initial string that's fairly easy to check for. But outside of that, outside of HTTP and DNS, it really didn't detect even IT protocols that had those ports changed. And even some like DNS, it detected sometimes and not other times. But there's a reason these tools do this. All of these tools will use that initial port because it's quick. You can load it up. You can open the PCAP. It opens fairly quickly. You can look through and identify those. It doesn't take a lot of time. This takes a little more time to go through and to look at. But we can actually identify those protocols and pull out those packets and those streams. So for my project, I did the 4 protocols, S7COM, Modbus, DMP3, and SIP. After I turned it in, I went through and added a UDP protocol, Ether S-Bus. Went through and added all of these. It's able to extract them. It's able to find them. So I can fingerprint these. And it's something that can grow. One of the reasons I added the Ether S-Bus is just to see how long it took me to add a new protocol. So I spent one night, about 3 hours, and then had one little problem where, actually, we'll go to challenges, and then I'll get back to what that problem was. So, challenges. So this was my senior project for my master's. The first one was I wanted to solve the world. After talking to my professor, we worked through how do you scope a research paper and a research project, go through some of this, helped me so not go from trying to solve everything to choosing a specific, to scoping it down to say this is specifically what you want to solve. You want to identify that this is a problem, show this is a problem, and then show how you can solve it. And so the next one, the program was originally written in Go. I wanted to learn Go. I hadn't written it much before for anything, so I started writing in Go. I chose their libraries. I started processing the packets. But when I did that modification, so when I did that initial modification where I took and I read the PCAP, and then I modified the ports and the CRC, I looked at those, checked, hey, are the bytes that I changed the only ones that changed? And they weren't. And I couldn't find out for a while why. And so I let it, I kept going, and then about halfway through my project, I was like, okay, I really got to solve why it's changing from one to the other. And so I went to look in the libraries and found out if the packet's out of spec, in this case, if it's not 64 bytes, which is the minimum length for Ethernet, then it pads it for you. So it adds extra bytes on the end of the protocol to make it within spec. And for the cleanness of my project to make sure that extra things aren't changed and that doesn't cause the problem, I couldn't have that. So I had to change. So I switched from Go to PCAP, or to Python. The big problem with that is I went from being able to parse all the PCAPs in my library in about 3 minutes to the Python taking 30 minutes because it parses it a lot slower, it does it a little differently, but it doesn't add those extra bytes when I do it. So figuring that out. And then the other challenge I kind of talked about is packets that contain little or no data are just too small to differentiate from other ones that are too small. So that padding of why I switched from Go to Python to fix making sure I'm not adding that path on. I actually ran into when I was doing Ether SBus, but the opposite way. I wasn't accounting for that padding being added when I was doing calculating my CRCs. So there were a few that were too small. I calculated my CRC, and it wasn't where I thought it was in the packet because they added those extra bytes for the padding. So then I had to go through and I had to calculate that. So after that first night of 3 hours, then it took me another half hour the next day to say, oh, this is what's going on. I need to account for that. And then not only fix that for this protocol, I have to go back and make sure that's not a problem while I didn't see it in my captures, I want to make sure it doesn't happen in other captures that I didn't get. The problem didn't show up where I had. All right, future work. So I did this work. I have lots of different things I'd like to do, like to change as I go through. So first, this is kind of a proof of concept code. There's lots of things that can make it so it's actually more useful to people. I'm going to increase the number of supported protocols so it can actually identify and pull out more. I'd like to go back to Go. It was much quicker, which makes it a much more useful tool. But half an hour, you can still run it, go do other things, start looking at the PCAPs, and then when it gets finished, you can pull up. But that 3 minutes seemed much more palatable to actually look. So you can run it and see what's going on. You can run it on multiple things. It's then something you can run more often in your environment. If it's taking half an hour, you might only run it for things that you specifically suspect but don't know. If it's a very short time, then you can run through it on a more regular basis. You can run things through it. Right now, it's all one long document or one long script. So all of the individual protocols I'd like to pull out into their own plugin. So you have one document for each protocol that can pull in. Then machine learning, just because people like machine learning, but also because I think it can be used for starting to characterize unknown protocols and pulling out specific fields. So you can feed it the bytes, and so each byte for each packet in a stream, and say, hey, what bytes are changing? How are they changing? Can we identify things like the length field? Can we look at different packets that are the same length and then packets that are different length and see which bytes actually changed in there and figure out what the different fields that are? So we can create a fingerprint for an unknown protocol. So we have a protocol that shows up. We don't know what it is, but now we have a fingerprint for it so we can see if it shows up anywhere else in our network or in our environment. Why this is important, going back a little bit to that previous talk, you have your malware, your testing tools, your things that might be running in your network that may run a different protocol that you haven't seen in your network. So now you may not know what it is, but you at least know when it shows up and you can fingerprint it and you can see it. So you can investigate it. Hey, we saw it show up here, and now it's starting to show up on other hosts. This may be something we need to look more into. Right now, I make one determination for each protocol. So I look at the whole stream. I look at what each was identified as, and then I output an overall, we think this is Modbus. What I'd like to add is we think it's Modbus because we looked at these specific fields. So you can kind of understand as you look at it and say, hey, they use the length field and the CRC. So it gives you a confidence of how confident we are in this matching. But we also had this other one that partially matched. So we can give that is kind of another thing. And then the other thing that I'd like to do is, as I said, a lot of these security tools, once you know what protocol it's running on, you can configure them to do that. I like to just have the output also output a Wireshark config file that says, hey, all these protocols are running on these ports. You can load it up into your Wireshark and do it. You don't have to actually go in and manually find all of the protocols and set what ports they're in. So let's see. All right. So one thing I talked about, I didn't show, but let's go to this room. No, not that. So here's our Protodetect. Yeah, so this is the CRC for one of the protocols. This is for the DNP3. You basically have a big table that it checks. We go through, but the main thing I wanted to show was actually running it. Let's run on just this one first. And so we run it. It goes through the PCAP. You can see for this one, this is that DNP3 one. It had a few packets, so there wasn't a lot in there. But you can see for each of these, it gives you the source, destination, the ports, and then a count of how many of that. And for this one, it says, hey, for that one, these are all the DNP3 we saw in this PCAP. And then, in addition to that, let's go up. PCAPs. Where did I put this? Modified. Okay. So here's the output. So we can come in. We can see we have that same source, destination, the ports. I pulled some other things out about the protocol. So the bytes, the time to live. Mostly that's for something else I kind of wanted to cover, where I actually fingerprint and identify not only the protocol, but the type of device. So if you're familiar with P0F, it looked at it and tries to fingerprint the specific devices. It uses specific fields for that. That's one of the other things I wanted to get to, but didn't to. But then we have the actual bytes, and then so for ones that had no bytes, I don't make a guess. For ones that do, I either put the protocol I guess it is or no guess. So I'm unsure for this protocol. For that, the hope is that we get to running the tool, and eventually we get to where there's very few that are no guesses, and then we can pull those out and say, hey, we have no guess, there's no parser for this, let's go figure out what it is and create one. So eventually you get to that, knowing your network, knowing everything that's on there, knowing all the protocols that you can see, and then if you see some that you have no guess for, you don't identify, you know those are something new. So let's, yeah, keep going on. All right. So we looked at the network protocols, kind of how they work, what they are. We looked at the 3 different tools, how they work to identify network traffic, and kind of how they break if you change those ports. And then we looked at Protodetect. Yeah, so that's the end. Thank you, and any questions? Oh. Yes. Network traffic, we kind of went over that. So it's how the two systems talk to each other. So it's what goes over the little blue cord that goes in the back of your computer and how it talks to that. So for example, if you have a Minecraft server that you're connecting to a server on, your game is going to send different traffic across the network to the server to say, here's how my character moved, I mined this block, kind of the different things that does that. So it keeps track of it. So you'll send it to the server will map it and then send it out to the individual client so they can kind of know what changes happened. Fingerprint is figuring out what protocol it is specifically. So is it one protocol versus a different? So you're looking at the different bytes to say that it's this specific protocol or another. Yeah. So I didn't for this. I wanted specific hard-coded OT protocols, but it is something that I think would work and could be there. And I think it's something that I'd like to see for like Wireshark. You can say, hey, open quick, and now it would be nice if there was just a button that says, hey, reanalyze this, take your time, figure out, map everything. Yes. Yeah. And so, no. Yeah. So, but I am looking at those like fields, um, but not for parsing the packets. For making the determination. Yeah. Any other questions?
So, you mentioned for, let's say, rep filing,
Mm-hmm.
you still see value in order to navigate tools like digital security service,
So the main reason is just to see what was there, kind of what was done. So they took an approach that they felt was novel and not. So I can look back at how they identified the protocols, kind of how they did some of that. But I kind of chose the Grass Mountain. That's an old tool. It wasn't deprecated when I started, but they deprecated it halfway through. And then Wireshark, that's standard. It's old. It's been used for a long time. It's been updated. And then you have the SenSaver, which is a brand new. It was released early last year. And so. Quick answer is no. Oh, not configuration files. That's about. Oh, it's not showing. There we go. That's about what you have. TC port and the values. Different protocols will have a little more, but I haven't seen any that let you get that granular on what's on there. So if you need that, if it's specific ports, this protocol is that. Likely what you'd have to do is actually extract the PCAP and extract the different streams out, and then for each one configure, which is still a pain. You'd still like to see them be able to do that, to say, hey, between these ports, 502 is this. Between these two hosts, 502 is this. Good. Mm-hmm. Yep. That's something I didn't look at. So I looked at their heuristics to figure out what things they were using, which is part of how I found out that most of them are using the port initially and using other stuff. So I saw some of theirs, looked through them, but I did not make it so I can drop theirs in or drop mine into theirs. Either way, that would go to that future work of things that I think are valuable. Wireshark's widely used, and if I can build it into that, that means lots of people are going to use it. Where if it's some script that someone wrote and uploaded to GitHub, then less people are going to be able to use that, and it's going to be of less value. So getting it in there would be good. It will be soon. It's not yet. So there's a few things I wanted to clean up before people could get it, but it will be out on my GitHub. So.